Okay, guys, so today is lecture 2.4. I'm going to share the notes with you. It should be a little shorter than last time. Last time we had a lot to go over. Let me move this around a little bit. Okay. So we're going to be talking about one-sided limits and continuity today. So this says one-sided limits is like it sounds. So you're going to talk about the limit from the left or from the right, which I think I'm a mirror image for you guys. So the left and the right. Left-hand limit, we see that, what do you notice about this symbol? Hopefully you can see it. Let me see if I can zoom. Here's the zoom. I don't think it's letting me zoom in. Okay, hopefully I'm going to highlight it for you to see. All right, so you see this right here, x approaching c, and has that little tiny negative sign. In calculus, or really in any math, when you see the negative, hopefully that makes you think from the left side, because the negative values would be on the left side. So this means x approaches c from the left. And then when you see it with the plus, that means x approaching c from the right. So the limit exists if and only if the limit from the left and the limit from the right equal each other, if they're going to the same spot. Even if it's an open circle, they have to go to the same spot and the limit exists. So we're going to look at this graphically. Use a graph to determine the limit if it exists. The limit as x approaches -6. Notice that there is no plus or minus sign. So that just means to -6 from both sides. So I'm going to get close to -6. 1, 2, 3, 4, 5, 6. I'm right here. It's continuous. So since it's continuous, it's just the same thing as the value f of -6, which is at 1. So that is 1. The next one says -5, but it has that little minus thing up here as a superscript. That means -5. So 1, 2, 3, 4, 5. Here's -5. But from the left means get on the left side of -5. Find the function and follow where it's going. And it's going up, 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 up. So it's going to positive infinity. Or you could say does not exist, because it's increasing without bound. Then this says negative infinity from the right. So now I'm going to get on this side. I'm going to come this way. And actually, I'm headed towards this open circle. And where's the value of this open circle? It is at 1, 2, 3, 4, -4. The next set, we have -5. Okay, so remember that the left and right need to be going to the same spot. So we're going like this. They're not going to the same spot. So we write that the limit does not exist, because this and this are not equal. Limit as x goes to -2. 1, 2. So here it's just the continuous. So it's just the value -1. I mean, well, not -1, 1. That's +1. Limit as x goes to 4 with the little negative means from the left. So 4, 1, 2, 3, 4, 4 from the left. This is the left. So you get on the left and you approach that number. We're going to this open circle, which is at 1, 2, 3, 4, 5. Now we have 4 from the right. So if I go to 4, here's 4, 1, 2, 3, 4. From the right is on this piece, and I'm headed towards this closed circle, which is at 3. And then this one is, do these two match? They don't match. So then this does not exist, because 3 and 5 do not equal each other. Limit as x goes to 6. 1, 2, 3, 4, 5, 6. Here we are. We have an open circle, but from the left and the right, they're both approaching that open circle, which is at 1, 2, 3, 4, 5, 6. That's at 6. So that's a little bit about how you look at one-sided limits graphically. I'm going to clear it and move the notes down. So now let's talk about how we find them analytically. You plug in -3. Well, what happens if I plug in -3? -3 plus 1 over -3 minus 3, I get -2 over 0. Oh, oh no. When you have a number over 0, that means you're going to infinity. It's either positive or negative infinity. Now, to figure out the sign of that, what you do is you plug in the number like I did, but then you have to think about this from the left of 3. Here's -3. If I'm coming from the left of -3, I'm on this side. So values lower than -3 are like -4, and anything in between these, like -3.1, if I'm getting closer, -3.01. These values close to -3, but from the left of -3. If I was to plug that in here, oh, I just realized I did that part. You guys, I imagined that was a plus sign. It's not a plus sign. I think that, I wonder if this example is written wrong. Okay, so that's a minus sign. So actually, if I do -3 plus 1 over -3 minus 3, -2 over -6, that is 1/3. So it'd be 1/3 either way, from the left or from the right, because there's no discontinuity there. This one, so let's say that instead it was what I was imagining in my head, -3 from the left, but it was x plus 3, okay? So what happens if I plug -3 in here is I get 0 on the bottom, which is what I was imagining the other problem was. That is a plus or minus infinity. The way you figure out which one is doing what I was demoing earlier. So imagine that I plug in something to the left of -3, like -3.01. If I plug that in here for x, and I added 3 to it, would the result be positive or negative? So if I take -3.01 and I do plus 3, I'm going to be very close to 0, but it's going to be a negative number close to 0. So as you get closer and closer and closer to 0. So a negative number close to 0. And the top is -2. So what's a negative over a negative? A negative over a negative is a positive. So this would be going to positive infinity. And there's an asymptote here at x equals -3. That's what is going on. There's a vertical asymptote at x equals -3, which we'll talk about more in just a minute. Now, let's do this example. I'm going to pause for just, okay, guys, sorry, I had to correct my my kids. Okay, let's do this example 3. So we're coming to 2 from the right side of 2. If we plug in 2, what happens? 3 times 2, because you always should substitute that number first just to see what happens. I get 6 on top, and on bottom, I would get the square root of 0. So I have my number over 0, which means this limit doesn't exist. It's either a positive or negative infinity, most likely. But let's kind of explore that a little bit more. So 2 from the right side of 2. So if I'm coming to 2, but from the right side of 2, that's like 2.01. If I square this number, I'm plugging in for x squared, 2.01 squared is going to be bigger than 4. So this overall number is going to be a positive number. You're also taking the square root of it. It needs to be a positive number. So this positive number means you're coming from the positive. You're dividing by a positive, very, very small number. Dividing by a positive small fraction, which means if you flip it and multiply, it's getting huge. It's blowing up to positive infinity. And then let's keep going. Okay. This one is a piecewise function. So it looks like a problem when we're less than 1 and a line when you're greater than 1. And it wants to know the limit at x equals 1. If you ever have a piecewise function, you need to look at the breaking point, like kind of like the handoff point. So where is this function changing from one function to the other? So I want to know the limit as x goes to 1, and it just so happens that that is where the function handoff occurs. So you're trying to see, I need to investigate, does the limit as x goes to 1 from the left, does it equal the limit as x goes to 1 from the right? And basically all that means is plug 1 into this top guy and plug 1 into the bottom guy and see if they equal each other. So if I plug 1 into that top piece, I get 1 plus 2, which is 3. And if I plug 1 into the bottom piece, I get 3. And 3 equals 3. So this is continuous. So the limit is at 1 is 3, since the limit from the left and the limit from the right both happen to be 3. Now this one, when I plug in 0, I get 0 over 0, which is indeterminate form. The absolute value of x is technically a piecewise function. What it is, it's the line negative x if x is less than 0, and x when x is greater than or equal to 0, okay? So if I was to make this a piecewise function, I would, if I divided this guy by x and divided each of these by x, that means that this function would look like negative 1 if x is less than 0, and 1 if x is greater than or equal to 0. Negative 1, so it's going to look like this. It's going to look like negative 1, and then it's going to hop up here, and then it's going to be 1. And so does that limit exist? Nope, because we're going to do 2 different places. So you would say this limit doesn't exist because the limit from the left is negative 1 and the limit from the right is positive 1. Similar thing to what's happening here, x minus 4. It's a very similar thing. But this one we can answer because it says 4 from the left. So x minus 4, let's just talk about that. 1, 2, 3, 4. That's a transformation of the absolute value shifted right 4. Okay, and so it's going to be the same thing where this divided by this is going to be positive 1, and it's going to be negative 1 from this side. So if I'm coming from the left, it's going to be down here, which is going to be negative 1. Because its absolute value just shifted over. Let's do this one, the greatest integer function. Oh, I'm sorry. All right, guys, so we want to find f of 2.1. Here's 2, we're at 2.1, so we jump up. So the answer is 2. 2.8 would also be in this line, which is 2. Negative 2.1, we come over down to negative 2, come over here. Negative 2.1 would be here at negative 3. Negative 2.8 is also at this line, negative 3. So that's just kind of being the greatest integer. This one, find the limit. Okay, so if the function's continuous, you just plug it in. And you know all polynomials are continuous. All polynomials are everywhere continuous. What's a polynomial, you might ask? It's something where it's like ax to the n plus bx to the n minus 1 plus dot, 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 etc. As long as all these guys are positive integer values, okay? So this is just x. Y equals x looks like this. It's not crazy. There's no jumps. There's nothing going on. So you just plug in 3. Negative 1. Again, x is continuous everywhere. So it's just negative 1. Secant. Okay, we're going to just plug in this pi over 2. Secant of pi over 2. And from last time, we kind of talked about unit circle. I have a separate video for that. Pi over 2 is here. Secant. Well, the values here, the coordinates are 0, 1. And secant is the reciprocal of cosine. So secant is the reciprocal of this guy. So the limit doesn't exist because the reciprocal of 0 is undefined, positive or negative infinity. 6 from the left of 6. So something smaller than 6. So like 5.9. If I plug in 6, let's just talk about that. 6 minus 6 would give us the natural log of 0, which is undefined because the natural log looks like this. As I get closer and closer to 0, it's going to negative infinity. So this number here would be a number that was really small to 0, but a positive number very close to 0. Okay, so it's from the right side of 0. And so that guy is going down to negative infinity. So you can write negative infinity or does not exist. Or you can think about this as a natural log function reflected and shifted, and that might also help. And you can always type these guys into a calculator if you're allowed a calculator on that particular portion, and investigate by looking at the graph. Okay, now this is a really important definition of continuity. So intuitively, hopefully you know what continuity means. If something's continuous, you don't pick up your pencil. Okay, so this line, continuous. This guy, not continuous, because I had to pause, right, and jump and pick up my pencil. So intuitively, hopefully you know continuous means you can draw it continuously without picking up your pencil. But that's not a mathematical definition. Okay? A mathematical definition is this. You have to have these three things. You have to have a value of the function. There has to be a point. This one, there has to be a limit. And this last one is that that point and that limit actually have to match up with one another. So there has to be a limit, there has to be a value, there has to be a limit, and the limit and the value have to equal one another. A function is continuous on an open interval, continues for every point in the interval. It's continuous on a closed interval as long as it's continuous from the right side and from the left side. So like this is continuous on the closed interval. It says if I come to A from the right, so on this side, see how it's continuous, I'm okay. And I come to B from the left, and it's closed in, it's okay, then it's continuous on the closed interval. Whereas something like this would not be continuous on the closed interval. It's continuous at A, but is it continuous at B? No, because this limit doesn't equal the value. The value is up here. This is an example where it's not continuous on the closed interval. Basically, at the endpoints, it needs to be continuous. Okay. Now we're going to talk about removable and non-removable discontinuities. So when you're looking at a graph, it's easy to see the difference. A removable discontinuity is a hole in the graph. So again, a removable discontinuity is a hole in the graph. That's what it looks like. It's like you just went, boom, like you plucked it out, okay? So you got tweezers out and you just pluck it out of there. Sometimes there's not a value, sometimes there is a value, but this is a removable discontinuity when you're able to remove it, which means what it looks like is like you can factor it out and simplify. Usually that's how you determine what the limit is in that case. A non-removable discontinuity, here's two examples. You have a jump in the graph. This is where the limit from the left does not equal the limit from the right. That's the fancy mathematical way of saying a jump. So you see this jump in the graph. That is a non-removable discontinuity. That's different than just this hole. Or you have going to positive or negative infinity. So there's an asymptote, a vertical asymptote in the graph. Okay, so removable hole, non-removable is jump or asymptote. All right. This, the x value for f is discontinuous. Okay, so the really easy way to just figure this out is where do you have to pick up your pencil? Okay, where are there these weird things going on in the graph? Hopefully you see the first one is at here. I'm going from left to right. I have to pick up my pencil here. So at x equals 0. The next one is x equals 3. The next one is at x equals 4. And it says y. Okay, why? This first one is because the limit from the left and the limit from the right don't equal each other. So this fails part 2 of the definition. The limit of x going to 0 doesn't exist because the limit from left and right don't match. This number 3 is it fails the third definition of that continuity. The limit does not equal the value at 3. The limit equals 3. but the value equals 2. And these don't equal each other. And 4 is that you don't have a value. F of 4 doesn't exist. This is part 1 of the definition. So those are the formal definition, how you would use that to explain why it's not continuous. What is the domain of the function? It's all real numbers except for x equals these numbers, 0. Oh, actually, no, hold on. All real numbers, what's the only place that's not defined? It's defined here. It's defined at 3. It's not defined at 4. So all real numbers except that x equals, except for x equals 4. Or you could say negative infinity to 4, 4 to infinity. Determine if it's continuous or discontinuous. Discuss the continuity. Okay. Okay, is this function continuous? This one is, I think the best way to explain this is to think about where it would have a problem. Okay, so assume it's continuous everywhere except where there might be a problem. And where you need to think about problems is if you have a fraction, you need to make sure that this bottom does not equal 0. So basically consider where it does equal 0. And wherever it does, that's where it's not continuous because you cannot divide by 0. If you have a square root, whatever function's inside the square root needs to be greater than or equal to 0. If you have a log, whatever's inside the log needs to be greater than 0. This is just kind of some function knowledge you should have. So I know that this function is continuous everywhere. Continuous everywhere except where the bottom equals 0. And where does that happen? That happens when x equals -1. So it's continuous everywhere except at -1. This one, let's see. I just need to check and see if they match up. And where you're checking is where it switches. It switches from the top function to the bottom function when x is 0. So does that equal? I have 2 equals 2, so check. So this is continuous everywhere. Because the other functions, these functions are both polynomials. Polynomials are continuous everywhere. So the only place where it maybe wasn't continuous was where it handed off from the top to the bottom function, and it matches up. So even though it's a weird shape, even though I have like a line and then I have a parabola, it's still going to be okay because they're matching at 2. This is just that you can add and subtract functions and still have continuous functions. You can multiply, you can take the product, you can divide, then all of these keep continuity. So where's this function continuous? It's continuous everywhere it exists. And it exists as long as I mentioned above, when there's square root, you have to make sure this inside is greater than or equal to 0, so greater than or equal to -3. So this is continuous everywhere from -3 onward. That's where it exists. And this function is continuous everywhere because this sign is like this. It's continuous everywhere. 8x is also continuous everywhere because it's a polynomial. And polynomials are continuous everywhere. So if I have a summation or a difference of continuous functions, the thing is continuous itself. So this is continuous everywhere because it's a combination of 2 continuous functions. Continuity of a composition function, it basically says if this function is continuous at c and then f of x is continuous at g of c, then it works out. So let's demo this. If I was to plug in f of g of x, so I'm taking g of x and I'm substituting it in for x. So sine of 1 over x squared. Sine is continuous for all values. This guy is only not continuous at 1. 1 over x squared has one problem. It's when its bottom equals, do you remember? 0, because you can't divide by 0, and that would happen at just 0. That's the only thing squared that gives you 0. So this would be continuous everywhere except x equals 0. Find the x if any where f of x is not continuous. Identify which of the discontinuities are removable. Okay, so it's removable if you can literally like remove it, which means factor and cancel. So let's see, if I factor the bottom, it's x plus 2 times x minus 3, because 2 times negative 3 gives us this negative 6. And if I add this negative 3x and 2x, I get negative x. This cancels out. So this one here on the bottom, remember when you have a fraction, you don't want the bottom to be 0. If you have f of x over g of x, you just want to make sure that this bottom is never 0. And when it is 0, whenever g of x is 0, that's where it's not continuous. So we have two discontinuities, one at x equals negative 2 and one at x equals 3, because those are the things that make the bottom equal to 0. And I was able to remove this one. So this is called a removable discontinuity. What this looks like is a hole in the graph. This one is called a non-removable discontinuity. And what it looks like is a vertical asymptote in the graph. Okay. This one, I'm just plugging in 3 from the left and right and see, does it equal? Oops, 10. So I get natural log of 1, and I get 10 minus e to the 0. E to the 0 is 1, I get 9, and natural log of 1 is the 1 point you should know in natural log, it is 0, and 0 does not equal 9. So is this continuous? But it's just not continuous at x equals 3. It's continuous everywhere else besides at 3. So we're going to say from negative infinity to 3, 3. Oh, wait, we don't have to get the domain. This question was just, where is it not continuous? So I would say that the discontinuity is at x equals 3. And it's a non-removable discontinuity because this is a jump in the graph. So what x value is at x equals 3, because you are having come into 0 from one side, you're going to 9 from the other side, and they don't match. Okay, intermediate value theorem, we're almost done. This ended up being longer than I hoped. Okay, I'm sorry guys, you're doing a great job staying with me. The intermediate value theorem is a fancy way of saying that you are something you already know. Okay, so before I even describe this theorem, I'm going to give you a situation, a true story from my life. So my dad is 6'8", and my mom is 5'3", and I'm like about the exact average of their heights. And I remember in 5th grade, at the beginning of 5th grade, so I was 11 at the beginning of 5th grade, is that right? Or was I 10? I think I was 10 at the beginning of 5th grade. I was 5 feet tall. Okay. And then when I was 11, I remember that year I grew 5 inches. So when I was 11, I was 5 feet, 5 inches. Okay. So say that's 6 feet. This is 5 feet, 5 inches. So my height's something like this, right? Now, my question is, was there a time I was ever 5'2"? Was I ever 5'2"? Hopefully you're saying yes. Okay. If I was 5 foot and then I was 5'5", did I pass through 5'2"? Yes, I had to pass through 5'2". Why? Because height is continuous. You don't just jump up over a height. You go through every single height, even if it only for an instant. You're going to pass through every height. Another really great example of this is temperature. Say that the low for the day is 48 degrees and the high for the day is 77 degrees. Was it ever 65 degrees? Yes. Even if you don't know exactly when it was, it had to be, because you know that 48 is down here, and then you know that 77 is up here, and is 65 in between those things? Yes. And so you know that it had to cross through 65. So this is the intermediate value theorem. And this is one of the first theorems you're going to learn in calculus of several. Intermediate value theorem says the big important condition is that f must be continuous, because if f is not continuous, it doesn't pass through every value. So that's the important part. F is continuous on this interval, closed interval, and you know that it says let n be any number between f of a and f of b. There has to exist c on this interval such that f of c equals n. I know that sounds very confusing. And in my example, the n value was 5, 5. Okay, so maybe that helps. That was like me saying 5, 5. And this was like saying 5 foot, and this was saying, oh no, this example was 5, 2. And this was 5, 5. So in this here, it's saying like, say I have some, all right, closed interval. This is A, this is B, and I have some value in between these. This line in, there's some value C between A and B that when you plug in C, you get the output of N. So let's do an example of this and hopefully it will make more sense. Explain that way there's at least 1 0 on the given interval. Your first thing, whenever you do this, you're always going to say f of x is continuous on 1, 4, or check and make sure it is. This one is, because the only place it wouldn't be continuous is at when x equals 0, it'll be undefined. And then you have to think about the tangent function and it's periodic. So is the tangent of pi over 4, I'm sorry, tangent of pi x over 10. I'm gonna graph that real fast. So I'm typing in tangent of pi x over 10. And I'm going to change my window to be between 1 and 4. And I'm trying to see if it's continuous on that interval. And it's not, okay? Tangent is not a continuous function everywhere. So since this is not continuous, then, hold on, I'm trying to see if it's not or if it's just my calculator. Hold on just a second. Okay, yeah, sorry, I wanted to pull up my calculator and it takes a little while to load, so I paused it. I wanted y'all to see what was going on. This works better than my old calculator I've had since I was in high school. So I went into y equals, I typed in tangent of pi x divided by 10, and then I changed the window to be from 1 to 4 because that's the interval we're on. And if you look at the graph, this graph is continuous everywhere between 1 and 4. So that means that it is continuous. So we can do the intermediate value theorem. So let's go back to those notes. So first step is saying that f is continuous. So f of x is continuous on the interval we're talking about was 1 to 4. All right, it's okay if it's not continuous everywhere. It just has to be continuous between the values it lists. And then all you do is you plug in the bottom value and then plug in the top value and show what they equal. Okay, so f of 1 equals negative 5 over 1 plus tangent pi over 1 over 10. F of 4 equals negative 5 over 4 plus tangent of pi 4 over 10. And then one of these should be less than 0. The other of them should be greater than 0. And then you show you pass through 0. So I'm going to actually go back to the calculator. Negative 5 over x. Let's share. Okay, so let's share this. I'm going to insert negative 5 over x. I'm typing the whole function now. Plus tangent. Okay, here's our graph. Oh, all right, we can't see. Need to change my window. The y min needs to be less than 0. So let's say negative 10 and see what happens. All right, there, now you can see it. Okay, so actually if you hit trace and then I type in 1, it will evaluate it at 1. What does it say? It's negative 4.65, yada, yada. You don't even have to say that. You just have to say it's less than 0. And then if I trace to 4, and up here, it's positive, and you can see it crossed through 0, right? That's what we were trying to make sure that we were showing, is that if I know that I have something and it's below 0, and then I have something that's above 0, does it cross through 0? Yes, as long as the function's continuous. It could cross through even more than one time, but we just want to prove it crosses through at least once. So let's go back. I gotta erase my stuff, but basically, sorry, you would say f of x is continuous on 1, 4. And then we showed that f of 1 was less than 0 and f of 4 was greater than 0. Therefore, f of x must equal 0 on the interval 1, 4 by the intermediate value theorem. So this is kind of a script for you. Every time you say f of x is continuous, you show it's less than, you show it's greater than, you say therefore it must equal 0 by intermediate value theorem. Because intermediate value, I forgot to talk about that, intermediate means in between. So it passes through all the in-between values between the value f of 1 and f of 4. Okay, last problem, guys. You all done a great job sticking with me. We're almost done. Same thing, apply. It says verify the intermediate value theorem applies. So verify it applies. I'm going to just go ahead and type this in the calculator to show you that it does. It should apply because the cubic function is continuous everywhere. You can take the cube root of negative numbers. You cannot take the square root of negative numbers. So the cube root looks like this. So I would say f of x is continuous everywhere. Then I say f of -9 equals, we'll plug in -9. -9 cube root of -9, what is that? That's not a perfect thing. The cube root of -8 is -2. What's the cube root of -9? -2 point yada yada plus 8, that's going to be a positive number. This equals 5.9199. Okay, f of -6 is the cube root of -6 plus 8. So -6 raised to the 1/3 power is -1.87 plus 8 gives me 6.18. Okay, is 6 in between these two numbers? Because I'm trying to show that it equals 6. Yes. So therefore, f of x must equal 6 on the interval from -9 to -6 by the IVT. So again, you're talking about it's continuous. You say you plug in the bottom number and then you plug in the other number, and then you say therefore it must equal whatever value as long as that value is in between the two outputs that you plugged in, because it must pass through all those in between values by the intermediate value theorem. All right, attempt the assignment. Let me know if you have any questions. And I plan on doing a video for the assignment to help with some I think that might trip you up. Okay, guys, have a good day.